Hey everybody, Mr. Bowman here. In this video we're looking at 3.13 probability concepts, and we're focusing on all the merit questions for the 2024 exam. If you're looking for more kind of merit excellence questions, check the link in the description below, and it's kind of got like a dump of all the achieved merit excellence questions broken down to the right level for you. So let's get straight into this question. So question number 24, this one was all about kind of Turnitin AI detection, and basically running through all the numbers, which kind of focused in this area of the question down here. So we were told that there is a 1% false rate. So what that meant is that's the probability of it being detected as AI given it was not AI. So that's why I write A dash there. So that's why, because it's false detection, right? It's falsely detecting it, which means it wasn't AI, but it detected it as AI. The next number here, 74% of the time it failed to detect AI writing. So that number there is the probability that it did not detect, so A dash, given it was A. And straight away, because I've got all these conditional formulas here, straight away I should be thinking probability tree. But the only thing is I need to find some kind of probability that splits from A to A dash initially before I can use those. And that's where this final paragraph comes in. Based on a confidential survey, it was thought that 22% of the pieces of work had content that was AI generated. So that's going to be the first of our split. So we're going to have AI was used or AI was not used by the students. And that there was 0.22, which means not AI was 0.78. We can now split to the second level. So this first split here, so if the student used AI, the Turnitin software either detected or did not detect that AI. And that related to this bottom probability here. So 0.74% of the time, so 74% of the time it failed to detect the AI. So that means this branch here is 0.74, which means the other 0.26 along the top was correctly detected. Same thing down the bottom. If AI wasn't used, the software would either detect it as AI or not detect it as AI. And in this case, it said it had a 1% false rate. So that means 0.01 is the probability for it being detected if it wasn't AI, which means the remaining 0.99 is sitting down the bottom there. Okay, so I've done my tree. Let's actually get into the bits of the question. So comment on whether a teacher should be concerned that a student is unfairly accused of cheating. So when I thought of that, I was like, oh geez, that's going to be quite difficult to figure out. But if you think about it in a probability sense, so that there is trying to find, well, what's the probability that AI was not used given it was detected as AI? So all of the people who were detected as AI, what's the probability that they did not use AI in this case? And it also might be interested to know, what's the probability that someone used AI given it was detected? And by comparing these two numbers, by evaluating the numbers, we can see, what's the proportion of people being unfairly accused of using AI or accused of cheating. So let's get into that, I suppose. So if you think of these two branches here, so the people who were detected as AI, it's going to be this branch up here and this branch through the middle. So we're really interested in these two probabilities here. So let's start off by finding the probability that someone used AI given they were detected. So the denominator is going to be the sum of these two branches, because they're the only branches that I care about. So it's going to be the top branch, 0.22 times 0.26, and we're going to add on the second branch, 0.78 times 0.01, and I'll make my fraction line a bit bigger. Of those ones, which of them used AI? It was that top branch there. So it's going to be 0.22 times 0.26. Okay, so I plugged that all into my calculator, and when I did that, I got 0.8786. And then, as always, probability, I always do a 4DP rounding. So now that I've got that, I can then find the other half of the equation. I can find Well, what's the probability that they didn't use AI but got detected as using AI? This calculation will be a bit easier, so it's going to be 1 minus the probability we just calculated, and that there is going to be 0.1214. Oh, I've written a 2 there. 0.1214. Okay, so now that we've done that, so we've done the maths, this is probably where our achieved mark is sitting, because it is a merit question. To actually answer the question is what we're going to need to do to get the merit here. And this one here is comment if the teacher should be concerned that students are unfairly being accused of cheating. And in this case here, 12% of the people being accused of cheating didn't use AI. And that, maybe the teacher should be that concerned. That's almost 1 in 8. So let's write a comment about that. So I'm going to write my answer over here now. So it'll be a written response for this section. So this means that approximately 1 in 8 1 in 8 people accused of using AI would not have used AI. Would not have used AI. As a result, the teacher should be concerned that students are falsely being accused. Okay, so that wraps up this answer. Okay, we're now on to question number 25, and this one here is a bit of a wordy one, so I'm just going to type up my response instead of the usual computer pen, so let's get rid of all that. And this question here, we've got a whole bunch of information. So we've got, in 2022, we've got 82.4% of Year 18s attained NCA Level 2 or higher, so that's a great percentage. And then we've got 83.4% of them achieved that in school, 4.1% of them achieved that in a tertiary or vocational settings. That's what this graph here means. So the beige colour there, that's all the people who achieved it in school, and the orange people there, this is when they achieved the NCA qualifications through another institution. And then the question we've got here is, based on the graph, is the suggestion that the total proportion of 18-year-olds with NCA Level 2 has increased between 2012 and 2022. So I guess what we're going to do is we're going to calculate the two probabilities first. So let's find the 2012 probability, and then after that we need to find the 2022 probability, and then we need to compare them. And because this is a merit question, there will need to be some kind of wordy element linked to context following that. Okay, so 2012, so we've got the two groups here, so that's going to be 71.2% plus the 6.1%, and when that is combined, that's 77.3%. So that means 77.3% of the people in 2012 had NCA Level 2 or higher. We're then going to repeat the same for 2022, so we've got 78.3 plus 4.1, and when that is combined, that comes to a larger 82.4%. So based initially just on the numbers, which I think is the achieved part of the question, just based on the numbers, we can see it has increased by 5.1%. So that's pretty good. However, that's a pretty basic answer, a Year 11, Year 12 stats question. So there's got to be more to it than that, I think. And when I looked into it, of note, I'm just going to do a third calculation. I actually looked at the 2018 number as well. So if you look at this 2018 number here, it was 80.4 plus 4.7. So 80.4 plus 4.7, and that there was 85.1%. And that's interesting. So that's higher than the initial number we've had. So I think there's two stories to tell from this graph. The first one is objectively, if you look at the start and end point of the graph, it has gone up. However, from 2018 to 2022, it's actually gone down. So I want to tell both of those stories as part of my answer. So let's get into that. So let's delete this stuff here. Let's type it up. So when comparing 2012 to 2022 only, the claim appears to be correct because the proportion increases from 77.3, increases by 5.1% from 77.3% to 82.4%. So that's the first story that I'm trying to sell. The next one is, well, actually, maybe that's not fully correct. However, this isn't the full picture, as the proportion actually peaked at 85.1% in 2018, and it has decreased until 2022. This suggests, or this casts a little doubt on the suggestion made. So I think quite a nice question if you picked up on it. But yeah, I think the achieved stuff would have been this comparison of 2012 to 2022 only, and then by picking up, well, that's not the full picture. There has been some decreases from 2018 onwards. That might have been the merit element of this question. So we are up to question number 26 now, and another merit question. This one was quite a simple question in terms of the text, but it was a bit trickier than it looks though. A player is playing two different games, A and B, so game B is going to be the subsequent question, so we're really focusing on game A here. For game A, if two dice rolls between 5 and 10 inclusive, then the player wins. Calculate the probability that the player wins at least 1 in 3 times. So I guess the first thing to figure out is we need to figure out, well, what's the probability of rolling between a 5 and a 10, which includes a 5 and a 10 if you're rolling 2 dice. So the way I did that is I drew a bit of a table here. I had 1, 2, 3, 4, 5, 6, representing the 6 outcomes of dice number 1. And then I repeated that 1, 2, 3, 4, 5, 6, representing the 6 outcomes of dice 2. So I'm considering the sample space here. And in this position here, that person would have rolled a 2 because it was a 1 and a 1. So I quickly added up all the totals. So all of those would have been those totals. We've got 3, 4, 5, 6, 7, 8. Reminder that 8 was because it was a 6 and a 2 that was rolled. And carrying on for the rest of my diagram, that's going to be 4, 5, 6, 7, 8, 9. And then we've got 5, 6, 7, 8, 9, 10. And then we've got 6, 7, 8, 9, 10, 11. And then we've got 7, 8, 9, 10, 11, 12. So that's my sample space. So from this, it's 6 by 6. So that means there's 36 different options. So my denominator is going to be out of 36. How many of them were between 5 and 10? So if you think of that, these are 5s. There's the 10s. So it's all of the numbers kind of sitting in that space. So the way I did that, I ended up looking what was outside of the space. So there's 3 there, and then there's 6 there. So that's 9. So that means there must be 27 sitting in there. And when I convert that to a probability, that's just 3/4. So it's 0.75. Okay, so that's the probability of winning between 5 and 10. And that was just one game. And this here is asking us for 1 win, or at least 1 win from 3 games. So I started mapping that out via a probability tree. So this is game number 1. You could either win or lose. Game number 2, you could win or lose. Again, win or lose. And then we got the last split, win or lose, win or lose, win or lose, and then win or lose. And then once I did that, I considered the outcome of each branch. So that top one there was winning 3 games. So that's definitely relevant to what we're doing. This time they won 2 games. Here they won 2 games. Here they won 1 game. So that's a tick. Here they won 2 games. Here they won 1 game. 1 game here, and then 0 games. So we don't care about that bottom one. So I thought what would be easier, instead of finding the probability of these and adding them all up, what I'm going to do is I'm going to find the probability of this bottom one here and subtracting it from 1, and that will then give me the probability of the remaining sections. So the probability of winning or wins at least one game, that's going to be equal to 1 minus loss. So remember, the probability of winning was 0.75, which means the probability of losing must be the 0.25, right? So that means it's going to be back down here. It's going to be 1 minus 0.25 cubed, because it would have been 0.25 times by 0.25 times by 0.25. And when I put that into my calculator, I get 0.984375. So quite a messy number. Could have rounded that, but I chose not to, just left it as a whole number. So we're now to question number 27, and that carries on a little bit from question 26. So what I've done is I've took a snippet of my dice table from the previous one. So breaking down the question, so when we got a roll of a 7, that is going to be a winner. And then we've got an immediate loser if they roll 2, 3, 11 or 12. And then finally, if you have no winner or no loser, the dice is kind of re-rolled again until you get a winner or loser. And the question here is asking us about the 3 games. So calculate the probability that the game is not lost before the third time. So basically what this question is getting at, this question is asking us to draw the big table for up to 3 games, and we need to find the probability of them losing before the third game. So that means the probability of them losing in the first game or losing in the second game. So let's draw that probability tree. I suppose let's start off with that probability. So the probability of winning was the probability of a 7, wasn't it? So that there, if you look at our table, that's these ones down the middle there. There are 6 7s out of the 36. So it's going to be 6 out of 36 or 1 out of 6. Then the next one is the probability of them losing this game. So that's the probability of a 2, a 3, 11 or a 12. If you look at that, we've got 2, 3 up there, 11, 12 up there. So that's going to be 6 out of 36. That's also going to be 1 out of 6. And then we've got finally the probability of, we'll call it an R for a re-roll. Basically, that's going to be any other number. So that's going to be 4 out of 6. So the remaining 4 out of 6 options. So each layer of our tree will kind of resemble that. So let's start off with the first game. So the first game, they can either win, lose, or have a re-roll. And we know the probability of winning was 1 out of 6, probability of losing was 1 out of 6, and the probability of getting a re-roll was 4 out of 6. We then have to repeat that, so we can stop these branches up here. So the winning and losing branch just stops because the game is over. But this re-roll branch is going to happen. It's going to split off again. So when they re-roll, they could still win the second game, they could lose the second game, or the second game could come up with another re-roll. Same probabilities because it's dice related, so it's not conditional on anything. So we've got 1 out of 6, 1 out of 6. There's a poorly drawn 4 there. And then we've got 4 out of 6. And then finally, this is the third game that the question's getting on about. So they could win, lose, or re-roll again. And again, that's 1 out of 6, 1 out of 6. And then we've got 4 out of 6 down there. So now that we've done all that, we need to get back to the question. So calculate the probability that the game is lost before their third game. So what that's trying to be is that's trying to find, well, it's going to be this branch here plus this branch here. So let's get into that, I suppose. So probability of lost before the third game. So that's going to be the first branch there, which is just easy. That's going to be 1 out of 6. So we've got 1 over 6, and we're going to add on the probability of the second branch, which is 4 out of 6 times 1 out of 6. So it's going to be 4 out of 6 times by 1 out of 6. And when I put that into my calculator, it got me 5 over 18. I could have converted it to a decimal, 40p rounding if needed, but I chose not to in this case. So that wraps up all the merit questions in this video. Hopefully you found them really useful. I really enjoy making these videos and breaking down questions for you all. Keep an eye out on the next couple of videos. I'm going to try to make a couple of weeks to kind of to help prep us a bit more for our upcoming mock exams and interview exams. Thanks heaps for watching. Thanks again.